Hey everyone, this is Brian, recording a briefing video for Project 3, which is all about trees and recursion. In Project 3, you're going to be writing several recursive algorithms to traverse and perform common computations on tree data structures. In the intro section, I talk about trees and how they work, as well as a quick overview of how recursion works. Remember that recursion is all about taking a big complex problem and cutting it up into smaller, simpler problems that we can then solve quite easily and combine those solutions to form a composite solution for the overall problem. Trees and recursion go hand in hand. Any node inside of a tree represents the root node of a subtree of the overall tree. In this way, we can apply recursive algorithms that apply to the overall tree to these simpler subtrees within the tree and then combine the solutions generated via recursion to form a solution to the overall tree. As always, to get started, go ahead and grab the Project 3 starter code and open it up in IntelliJ. Let's take a look now at the Project 3 starter code. I start out by giving you a binary node class. The binary node is as we've seen it in the lecture. It's just a container for a left and right reference, as well as a payload value. I've given you some simple constructors to work with, as well as an enum declaration called direction within the binary node. You're going to be using these left and right enum values later when you write your pathing algorithm for the binary tree, but we'll get to that later. We're going to be using binary node to represent nodes within a binary tree that you're going to be writing algorithms against. Let's go look at some of those algorithms now. The first set of algorithms we'll be writing are for depth-first binary trees of traversal. We've learned how depth-first search involves looking at the deepest nodes within the tree before looking at other nodes surrounding that node. There's three strategies you can apply for binary trees to perform a depth-first search: pre-order, in-order, and post-order traversals. In all three of these method signatures, I ask that you take in a root node and you produce a list of nodes in the order that is specified. So for example, for the in-order search, I'd like you to return a list of values, that is these type t's inside the tree, in the order of left node, parent node, and right node. Of course, this is going to have to be a recursive function, so you will need to combine the lists that are returned recursively with the lists from the calling function. In order to do that, you may fulfill the list via either the linked list or array list, it's your preference, and you may use the add all method to copy and append all the values from one list to another. With these three depth-first searches, once you solve one of them, you're going to end up solving all of them pretty quickly, because it's just a matter of reordering the way you append items onto the list that ends up getting returned. You may be conscious of how the add all method essentially turns this algorithm into n squared or worse. For the purposes of this project, I'd like you to more or less ignore runtime cost. I do want you to be conscious of making unnecessary calls to recursive functions and avoiding those, but we're going to treat these list structures as sort of abstract entities that have fast append, so don't be too concerned about what you have to do to actually form the list structures themselves. Next up, we talk about binary search trees. Remember that a binary search tree is a special kind of binary tree that is structured in a way such that for every parent node, all the nodes to the left of that parent are going to be less than itself, and all the nodes to the right of the parent are going to be greater than itself. For binary search trees, I'd like you to write the algorithm binary search as well as insert. Binary search is going to go find a number within a binary search tree, and insert is going to go insert a new binary node into a binary search tree as a leaf node based on the binary search tree itself. Then there's a couple of other algorithms I'd like you to write for binary trees. An equals method, that's going to ask if two binary trees are the same structure by value and structure. Then a path method, that's going to take in a root binary node and look for a value within the tree and return a linked list of directions that lead from the root all the way up to the value. The path method is probably going to be one of the most complex methods you'll implement in the project, so if you have trouble with it, I recommend you actually move on to some of the other methods first to get more practice, and then come back to it later. So that's an example of the methods that you'll be implementing for binary trees. The other half of this project involves methods for trees in general that may have 2 or more children. We're going to use the tree node class to define nodes within a tree that can have an arbitrary number of children. Let's go take a look at that now. In tree node, rather than just having a left and right reference to point to the children of the node, I have an entire array list worth of children. I also have that payload value. In order to examine the children within the tree node, you may use some of these public methods like addChild and getChild. addChild simply appends items onto the children array list, and getChild is simply an index lookup function for whatever child is at a given index. Note that this children field is public, so what I recommend you do is actually when interacting with this tree node to traverse all the children of the tree node, just use that for each loop construct that we've been talking about throughout this class. The tree algorithms are going to be a little bit more complicated because they involve traversing all the children, but the overall pattern of recursion is still the same. You're going to be writing some base cases, and then you're going to be combining the solution returned by the recursive cases in order to form an overall solution. Here are some of the problems that I'd like you to solve. Max, which should go find the maximum number inside the tree. Min, which should go find the minimum number in the tree. Leaves, which is going to go return a linked list of nodes that are all the leaf nodes in the tree. Recall that a leaf node is a tree node without children. Count, which is going to count the number of nodes in a tree. Depth, which determines the maximum depth of the tree. Equals, which is going to determine if 2 trees are the same by structure and by value. Breadth first search, which is going to go perform a breadth first search of a tree and return a linked list of nodes in search order. This is actually one of the this is actually the only algorithm in this project that doesn't actually involve recursion. You can do so iteratively using a queue structure, the Java linked list, or the Java library queue that is, to store and retrieve nodes in the queue order rather than depending on the stack, which we implicitly do whenever we write recursion. I'll give you a quick link to the official Java queue documentation, as well as some tips and guidance on how to use it. Then finally, for the trees that have any number of children, I'd like you to write another path function that's going to go figure out the path of nodes that leads from the root to the value we're looking for. Again, the path method is probably going to take you the longest among all the methods that I'm asking you to implement, so I suggest you leave it for the very end. Note that there is a small distinction between the method signatures for the path of the binary tree and the path of the non-binary trees. In the path method for binary tree, I'm asking you to return a linked list of directions. Remember that direction enum that we mentioned? How it has values left and right that you can assign? For this path method, I'd like you to return instructions that tell a client how to reach a given node from the root node. For the trees that have an arbitrary number of children, I'd like you to instead return a linked list of nodes that represent the path itself. So when you discover the path to reach a given value, you should procure the nodes that lead up to that value. This is different than the linked list of directions because the directions simply point a client towards the right direction, look left or look right. Whereas over here, I'm actually composing a list of nodes themselves that are going to start from the root all the way up to the value I'm looking for. This project does have opportunity to earn bonus points. There's a total of 15 test cases, one for each method. You only need to pass 14 to get a score of 100. If you can pass all 15, you'll get 10 bonus points for a total score of 110. As usual, there are run scripts included that can give you a grade estimate right away, and it's fully integrated into IntelliJ, so you can go run the test individually or all at once. Don't forget, I also list out these critical analysis questions at the bottom, which are intended to make you think about why and what you're doing with these project questions and your choices that you're making during implementation. These are the kinds of questions that you might see on an exam. Okay, That should be enough to get you started. This project isn't too much different from the other projects in terms of structure and how they're done, so I trust that you're familiar with that already. As always, if you have questions, don't hesitate to email me or ask them on Piazza so I can help out the other students. Thanks for listening, and I'll talk to you next time.